Dark matter is the idea that there is this different form of matter which is almost undetectable, but 5 times as prevalent as regular matter. Yes, this sounds extremely implausible, so why do we think that dark matter exists? Well, when we look at the universe, at galaxies and galaxy clusters, their movements are at odds with our understanding of gravity. Galaxies rotate too quickly, clusters hold together even though they shouldn't, stuff like that. But throughout all of history, observing something in the universe that doesn't make sense to us was very common. The usual solution to this has been that there were objects that we could simply not see at the time because our telescopes weren't good enough or we were lacking instruments to see X-rays or infrared. So that was our go-to explanation in this case too. We just figured there must be some additional mass out there, and quite a lot. And as we couldn't see it, we called it dark matter. But there is another possibility, of course. What if there really is no invisible mass? We know that our physical laws work perfectly well here on Earth and in our solar system, but at larger scales, things could be different. Maybe our current laws and models are simply wrong. It's not outrageous to believe that there are new effects at new scales. In fact, that's a recurring experience in physics. It's absolutely not the case that there is a ban on such ideas and people must accept dark matter. But it's really hard, it's really difficult to come up with a new theory that contains all the old correct results from Newtonian mechanics and Einstein's general relativity, and also explains some new behavior we have observed. So there are a number of dark matter alternatives. It's just that most of them aren't really well worked out and/or contradict some data. The most successful approach so far has been modified Newtonian dynamics, or MOND for short. This was published by Mordechai Milgram in the early 80s, in response to the most ubiquitous problem of this time, rotation curves of galaxies. Instead of postulating lots of invisible mass, Milgram's approach was to adapt the laws of dynamics, the good old F equals ma. In high acceleration regimes, like within our solar system, this would remain as it is. Only for low accelerations at around 10 to the minus 10 meters per second square, this would be changed to... This acceleration A0 would be a new constant of nature. This so-called Milgram's law can be framed in different ways, but the most common one is to interpret it as a modification of Newtonian gravity. This idea would split our universe in two. The Newtonian realm, where all our current laws hold, and the MOND realm, where different dynamics apply. Mathematically, there is an interpolating function that switches between the two. So basically, MOND keeps everything the way it is, except that it changes how accelerations work at very low values. This makes no difference to anything we can experience, but it does have a profound effect on very large structures, i.e. galaxies. As MOND was specifically designed to model rotation curves, it will not come as a shock that it's pretty good at modeling rotation curves. When we look at a galaxy and assume that all the mass is in the stars, we can count them and deduce the total mass of the galaxy and where it is located. So we would expect a spiral galaxy to rotate in a very specific way. And stars within the galaxy should have typical velocities depending on their distance from the galaxy's center. Very much like the planets in our solar system. But when we measure these velocities, the picture is very different. Velocities do not drop off towards the galaxy's rim, but they keep steady or even grow, which makes no sense in our model. And to make this point very clear, the question is not why are those stars moving so fast? The question is very much, seeing as how fast these stars are moving, how on earth are they still within the galaxy? It's like the moon is orbiting the Earth, held by Earth's gravity. Now, if the Earth vanishes and you just see the ISS and the moon is still rotating around it, you know something is wrong with this picture. Either the Earth is still out there, just hidden or dark, or gravity works completely different to what we thought. And it turns out that if you replace Newtonian gravity with MOND and choose the correct value for A0, the model actually predicts the same rotation curves that we observe. And this is not just selective curve fitting, the same value of A0 works very well for all rotating galaxies. And somewhat related to that, there is the Tully-Fisher relation between the total mass and the velocity of typical stars in the flat part of the rotation curve. It turns out that this mass is proportional to the velocity raised to the fourth, which you can directly deduce from MOND. And there are some other relations concerning the rotation or the scaling of galaxies, which are extremely well modeled by MOND. And you cannot simply dismiss that because the fit to the data is quite remarkable. So there seems to be at least something here. While MOND has several things going for it, there are also several shortcomings. First off, it's a purely empirical patch for an existing theory. There is no physical explanations behind it. It's just, if you do this mathematical adaptation, the curves will fit better. But nobody can say what this change means in terms of physics. To be fair, it never was supposed to be. It was only ever meant as a simple empirical fix to Newtonian gravity. And of course, Newtonian gravity itself has been superseded by general relativity more than 100 years ago. And a lot of the effects that we know today are purely relativistic. There are some relativistic models of MOND by now, the most well-known of these being TeVeS by Jacob Bekenstein, which can reproduce phenomena like gravitational lensing and some cosmological background behavior. However, there are also other results like the gravitational wave measurements or effects from cosmology that TeVeS cannot model. And there are even discussions whether stars, just normal stars, would even be stable under TeVeS, so I guess you could say it's a bit of a mixed bag at the moment. The biggest issue with MOND is, however, that while it's pretty good at describing the behavior of galaxies, it fails as soon as you go to galaxy clusters. One particularly famous example is the bullet cluster, which some people even see as having disproven MOND. But that's a slightly longer topic, so I will go into that in a separate short. The main thing though is that MOND cannot by itself explain the behavior of galaxy clusters. It also requires additional invisible mass. So yeah, dark matter. On the one hand, you could say that if a model was supposed to get rid of dark matter, comes back with dark matter, at what point do you declare failure? On the other hand, it does require a lot less dark matter. And maybe the eventual solution to this will be that we do have new physics, but we will also need some dark matter, just not as much as we believe right now. In general, you could say that MOND was worked out in the 80s to fix the biggest problem of the 70s, the rotation curves, but it fit less and less over time for everything new we found in the decades since. But let's keep things in perspective. MOND was never intended to be a full physical theory to replace Newtonian gravity or Einstein's general relativity. It was more of an attempt to see how much you could fix with even just a simple change. Basically, it just takes classical mechanics and slightly tweaks how accelerations work at a certain level. And it clearly has many flaws, but it was a courageous departure into a completely new direction. And the longer the search for dark matter only turns up negative results, the more it makes people reconsider whether a different approach isn't more viable. This different approach will probably not be MOND though, because it has so many issues that it's almost certainly incorrect. But that is not the point here. Bohr's model of the atom was also incorrect, and it only worked for the simplest atom of all, hydrogen. It was way too simplistic and made assumptions not based on any known physics. But it also worked. It could explain a little piece of the puzzle, and it was a stepping stone to real, proper quantum mechanics later. And MOND might turn out to be something similar, something that moves us in the right direction to some new complex physics at galactic scale. Then again, maybe not. I'm Chris, and this is Physics But Awesome. At the moment, I mostly do stuff on quantum mechanics, quantum computing and cosmology, so if you like this video, subscribe for more.